Greetings and welcome back. Today we're going to talk about comparing means among two populations again, but instead of having two samples paired from the two populations being compared, we're going to have two samples from two independent populations, or even more. So what we're going to cover in this series of lecture pieces is we're going to talk about confidence intervals for the mean difference when we're comparing samples from two independent populations, i.e. unpaired populations. And we'll talk about this in the context of the two-sample t-test, which will also include a hypothesis testing p-value component. And we'll look at a few examples of this in action. We're going to briefly discuss, and this is optional, something called a non-parametric alternative, the Mann-Whitney test, which can be used in place of the two-sample t-test. And then we're going to talk about comparing means among more than two independent populations with one method, something called analysis of variance, frequently represented by its acronym ANOVA. So let's kick this off by talking about the two-sample t-test and the resulting confidence interval we get as part of the procedure. And we're going to use an example from the New England Journal of Medicine from a few years back to talk about this and get this going. And this is from an article entitled "A Low Carbohydrate as Compared with a Low-Fat Diet in Severe Obesity." In this study, 132 severely obese subjects were randomized to one of two diet groups, and subjects were followed for a 6-month period after being put on one of the two diets. They were randomized to either a low-carbohydrate diet or a low-fat diet. At the end of the study period, subjects on a low-carbohydrate diet lost more weight than those on a low-fat diet. 95% confidence interval for the difference in weight loss between the two groups, negative 1.6 to negative 6.2 kilograms, with a p-value of less than 0.01. So what we're going to talk about in the next two sections is how to get that confidence interval and how to get that p-value. So the original scientific question posed by the researchers who designed this study is weight change associated with the type of diet, low carb or low fat? And this was of interest a few years back. It's now 2008 when I'm talking to you, and this was a big deal about 4 or 5 years back, the low carb diet phrase, which is still, people still adhere to different forms of low carb diets. They're very popular. And the claim was that they were associated with weight loss. So in this study, we had 64 patients in the low carb group and 68 patients in the low-fat group. The mean weight change for the post-diet less pre-diet for those in the low-carb group was negative 5.7 kilograms. So on average, subjects in the low-carb group lost nearly 6 kilograms of weight in the 6-month period, as compared to a weight loss of negative 1.8 kilograms in the low-fat group. And the standard deviation of the weight changes is given here. In the low-carb group was 8.6 kilograms, and in the low-fat group it was substantially lower at 3.9 kilograms, less variation. So we could go ahead, if we were trying to figure out whether diet type was associated with the magnitude and direction of the weight change, we could go ahead and compute confidence intervals for the weight change on average by each diet group. So if we did the low-carb group, we could go through the X-bar plus or minus 2 standard errors, 2 estimated standard errors approach. You can see the math here, and the 95% confidence interval for the true average rate change, had we put every severely obese patient on the low-carb diet, is between negative 7.8 kilograms and 3.5 kilograms. After accounting for sampling variation, subjects in this group overall could have lost anywhere from 3.5 to 7.8 kilograms on average. And similar approach for the numbers from the low-fat group give a 95% confidence interval from negative 2.7 kilograms to negative 0.9 kilograms. So two things to notice. Even after accounting for sampling variability, in each of the groups, there appears to be some evidence of true weight loss at the average level, because both those confidence intervals for weight loss or weight change in each of the groups include only negative values indicating a loss and don't include 0. Additionally, if you notice, the two confidence intervals do not overlap. They do not share common values. This suggests that there may be, on top of it, a significant difference in the amount of weight change on average between the low-carb and the low-fat diet group. So in statistical terms, we're sort of asking, is there a non-zero difference in the average weight change for the subjects on the low-fat diet as compared to subjects on the low-carbohydrate diet? And what we actually observed was weight loss in both groups, so we could talk about this in terms of difference in average weight loss. And we said the 95% confidence intervals for each diet group, mean weight change, do not overlap. But how can we actually quantify the difference in average weight change and put confidence limits on that? The comparison of interest here is not paired, by the way, even though within each of the diet groups we actually computed a paired measure, the difference in weight after 6 months on the diet to before. What we're ultimately interested in comparing is these changes between two independent groups, those on the low-carb diet and those on the low-fat diet. So how do we calculate a confidence interval for the difference? And how do we get a p-value to determine if the difference in the two groups is statistically significant, or to actually put a face on statistical significance, because we saw some evidence that with the non-overlapping confidence intervals. Well, let's just review some ideas. Since we have large samples, we know the sampling distribution of the sample means in both groups are approximately normal. And it turns out, while the difference of the quantities, each of which are approximately normally distributed, that difference also has a normally or approximately normally distributed sampling distribution. So the big news here is, again, we have a central limit theorem hookup that tells us what would happen had we done the study many times without having to do that. It tells us, look, the sampling distribution of the difference of two sample means, when each is based on a large sample, approximates a normal distribution from pairs of random samples across all possible random samples from each population. And this sampling distribution is centered at the true mean difference. I'll just generically refer to that as mu1 minus mu2. So let's just illustrate this pictorially with a simulation example. Here I simulated the sampling distribution of the sample mean weight change in the low-carb diet group. And what I did for the simulation was I pretended that the actual mean difference we observed, a negative 5.7 kilograms on average. I pretended for the moment that was the truth at the population level. And then I simulated taking 1,000 random samples, each of size 64, from a population with that characteristic. And here's the distribution of those sample means. So there's 1,000 sample means in this picture. And you can see it's roughly centered around negative 5 something. And it has a somewhat symmetric bell-shaped look. It looks normal-esque. I did the same thing. I simulated the same thing for the low-fat diet group. And you can see that it also looks relatively normally distributed, the 1,000 random samples, each based on 68 observations from the population, which I assumed had a true mean difference of negative 1.9 kilograms, what we actually observed in our study, just for simulation purposes. But you can see the spread is a lot thinner. Even though the sample size is about the same as in the low-carb group, the actual standard deviation of the individual values in this group was a lot lower, and that contributed to a lower standard error or spread in the sample mean values. And then what I did was I just took sample 1 from the low-carb group and matched it up against sample 1 from the low-fat group and took the difference in those means. And then sample 2 from the low-carb group, sample 2 from the low-fat group. And I did that for all 1,000 non-paired samples, just lined them up next to each other. There was no inherent pairing, just the order that they came in. And this is the distribution of the differences in those sample means. So what do you notice about that? Well, it's certainly normal-esque as well. And it splits the difference between the other two curves. And what about the spread? Well, it turns out here's a box plot representation of the three distributions, the simulated sampling distributions. And you can see that on the far right-hand side, that's the box plot of the 1,000 differences in sample means from the 1,000 random samples from each of the two populations, based on the same sizes as the study that we based this on. You can see that the spread of it is more like that of the low-carb group than the low-fat group. And in fact, it turns out it's going to be a little bit wider than that on top of things. And you can see it splits the difference between the two in terms of where it's centered. So we'll talk more about the reasons for that as we move on. But this whole thing about the central limit theorem kicking in gives us the same logic that we use for computing a confidence interval for a single mean when we're doing a difference in mean between two groups. Our most general formula for a confidence interval that we've seen before repeats itself here. We take our best estimate from the sample and take plus or minus 2 standard errors or estimated standard errors of our best estimate from the sample. So the best estimate and that's because of the approximate normality we just demonstrated through simulation, which can be shown mathematically in the context of the central limit theorem. We can take that on faith. The best estimate of a population mean difference based on 2 sample means is the difference in sample means. That's the best we've got from our studies. So we have the starting point for this confidence interval. So I'm going to let X1 bar here represent the sample mean weight loss for the 64 subjects on the low carbohydrate diet. And X2 bar, the mean weight loss or change for the 68 subjects on the low fat diet. And so X1 bar minus X2 bar is the difference in average weight change, low carb to low fat. So in our study, the one we started with, this mean difference was the negative 5.7 kilograms change on average in the low carb group minus the negative 1.8 kilogram change on average in the low fat group, for a difference in means of negative 3.9 kilograms on average. So that implies that those in the low carb group had a change of 3.9 kilograms lesser than those in the low fat group, which indicates that they had a greater weight loss. So the formula for the 95% confidence interval for the true difference in mean weight change, had we put everyone on low carb versus everyone on low fat, we take our estimated difference, negative 3.9, and add and subtract 2 standard errors, where this notation here, SC, followed by X1 bar minus X2 bar in parentheses, is the standard error of the difference of the 2 sample means. So all we need to do to finish this is figure out how to get the standard error of the difference for the 2 sample means. And the standard error of the difference for 2 independent sample means is calculated differently than we did for paired designs. With paired designs, basically, we suck the wind out of the excitement right away by taking 2 samples and reducing them to one set of differences, and then treating it like a single sample thing. We can't do that when there's no inherent pairing between the 2 samples from the 2 populations we're studying. So statisticians have developed formulas to theoretically solve the problem for this standard error of the difference. And these depend on the sample sizes now in both groups and then the standard deviations in both groups. And something we alluded to in that simulation results just a few slides back is that the spread in the difference of sample means is greater than the standard error of either of its parts. It's greater than either the standard error of the single X1 bar or the standard error of X2 bar. And even though we're looking at a difference, the uncertainty is greater than the uncertainty of either 2 quantities involved in that difference. And I'm going to put this out there, and we can discuss it in the bulletin board or live talk, but I want you to think about why that might be. Remember, we're comparing 2 independent groups. So it turns out, building on that idea, the variation from the independent sources here can be added, even though our quantity of interest is a difference in 2 means from 2 independent samples. So again, building on the heels of that last slide, why do you think this is additive if we're taking a difference in means? Why do you think the standard error or the uncertainty in the difference in means is an additive function of the uncertainty in each of those means that we're taking the difference between? And it turns out formulaically it's equal to the square root of the true population standard deviation from the population in which sample 1 was taken squared over the sample size that X1 bar was based on, plus the true population standard deviation from which sample 2 was taken squared over the size of sample 2. Of course, again, we don't know the true population standard deviations. That's why we're doing this study. So we're going to estimate those with the sample standard deviations from sample 1 and 2, respectively. And so we can estimate the standard error of the difference using information from 2 samples only by replacing those sigmas with S. If we actually re-express this, it's just the square root of the standard error of X1 bar squared plus the standard error of X2 bar squared. So it actually is an additive function of the uncertainty in each of those 2 sample means. So just to recall the data from the weight loss study here, if we plug our numbers into this formula with the estimated standard error of the difference in these two sample means, one based on 64 observations and the second based on 68, is about 1.17 kilograms. So to complete the example now, we've shown that we can estimate the sample mean difference from two samples, which is our best guess for the true difference between the populations from which the samples were taken. We've now seen we can also estimate the uncertainty in this difference in sample means. We put it all together in a confidence interval by taking our sample difference in means and subtracting two estimated standard errors. And when you play this all out, it gives a confidence interval for the true average difference in weight changes, low carb group to low fat group, between negative 6.2 kilograms and negative 1.6 kilograms. So what this says is even after accounting for sampling variability and uncertainty, this suggests that on average, those in the low carb group will lose anywhere from 1.6 to 6.2 kilograms more than those on the low fat diet. Because both these numbers are negative, indicating that the weight change is lesser, more negative, if you will, for those in the low carb group than the low fat group, which in turn translates into more of a weight loss. So I'm going to take now quotes from the article, and the article is posted in the online library as well for you to look at. It says subjects on the low carbohydrate lost more weight than those on a low fat diet. This is the quote we started with. 95% confidence interval for the difference is that one we just showed, and a p-value of less than 0.01, and we'll get to that in the next set. So those on the low-carb diet, here's my take, lost more on average by 3.9 kilograms. After accounting for the sampling variability, this excess average loss over the low-fat diet group could be as small as 1.6 kilograms or as large as 6.2 kilograms. And see if you can convince yourself of that, translating those negative differences in weight change into weight loss. This confidence interval does not include zero, suggesting a real population-level association between type of diet, low carb versus low fat, and weight change.